Okay, so surface independence. Last time we were talking about this thing called path independence. Right? Path independence is a really interesting property. And let me go to our diagram here. Remember, we have our completed diagram. Well, mostly completed diagrams. There's a little bit more I'm going to add to them soon. But diagram showing the various boundary theorems that we have. Right? And I'm going to try to draw a picture on here, a sort of a schematic chase, if you will, of what does path independence look like. So, first thing I'd like to note, path independence is a property of a vector field. So we're talking about a vector field of which we will be computing line integrals. So here's this is the place in the diagram where the objects we're talking about live. And they have this feature. This is what path independence says. Path independence, not all vector fields are path independent. But if you have a path independent vector field, that means that if you have two curves, different curves, that have the same boundary points, in other words, they start at the same point, they end at the same point, right? Then those two line integrals give you the same value. So this is my little cheap diagrammatic representation of what it means for a vector field to be path independent. Okay, now we saw that a vector field is path independent if it is a gradient of something, or said differently, if it has an anti-gradient. Right? This is a neat fact. Path independent equivalent to being a gradient. And we further saw that another equivalent condition is that a vector field that is a gradient, that is path independent, has the feature that the curl is 0. All right, so we have this collection of vector fields, and they have any vector field that has any one of these properties has all three of these properties. Right, and that's kind of a neat fact. So let me point out, this is pretty unsurprising, I'm going to go ahead and say it anyway, that this little discussion of these various properties that a vector field in R3 might have, same thing in R2. Well, analogies, not exactly the same, but analogies. So with vector fields in R2, there is no curl, but there's a Green's operator. Right? And so Green's operator is the thing that is 0 when, let's see if I can get this to line up better. There we go. The thing that is 0 when you have a path independent vector field. All right, that's no surprise because, well, look, if you're talking about line integrals in R2, line integrals in R3, the pictures are pretty much the same, except, to go from R2 to R3, just draw yourself a third axis. I mean, it's not surprising that it ought to work. Here's the really surprising thing, though. Not only is this idea of path independence equivalent to a comparable notion over here, it's also equivalent to a comparable notion over here. That's really unexpected and surprising. So, now I'm going to use the diagram chase to talk about, following the pattern, assuming the pattern holds, what would we expect to be true about certain vector fields, of which we might be interested in fluxes. Well, what we would expect is that some of these vector fields would have the feature that sometimes you have two surfaces that have the same boundary curve, that the fluxes of the vector field through those two surfaces would be the same. And that's true sometimes. We're going to talk about that in a couple minutes. We're going to also find that such vector fields are curls. Or said differently, such vector fields have anti-curls. And we are also going to find that such vector fields have the feature that their divergence is equal to 0. Okay. So this is one of the things I love about the diagram. When you organize these operators and objects and constructions in this way, the patterns are overwhelming. Right? So any pattern that you notice in some context of the diagram, you can take that pattern and just take a step to your right, and same thing. Okay, so now this is just bald assertions here at this point. I just wanted you to see the picture. I wanted you to see the pattern about how, by the way, this is what we're going to call surface independence. What I have in green here, this property, surface independence. So as we go through and start talking about surface independence, I want you to note the very strong pattern, the very strong analogy that it holds with path independence that we just got through talking about last time. Okay. So, in fact, just for, I mentioned largely for humor value, but also because it's true, when I wrote this section on surface independence, the very first thing that I did is I went back to the section I had written the previous day on path independence, and I did this massive copy-paste. And then I went through and I found, everywhere I saw the word path, I wrote surface. And everywhere I found, the word boundary points, I wrote instead boundary curve. And that wrote a large part of this section. Right? It's very, very strong analogy. It's not completely, and there's obviously other things that are different. Okay, so here we go. We're going to first note Stokes' theorem. Y'all remember Stokes' curl theorem? We talked about this over the last couple of days. By the way, let's go back to the diagram real quick. In discussing surface independence, we are starting with Stokes' theorem for largely the same reasons that with path independence, we started with the fundamental theorem of line integrals. And so that's, in fact, if you knew nothing about surface independence, just this comparison, this left-right comparison here would suggest that, hey, maybe the fundamental theorem of line integrals is so useful last time. Hey, maybe we should think about Stokes' curl theorem and go from there. Okay. All right. Make that bigger. There we go. Okay. All right. So Stokes' curl theorem. Here it is. And notice what this says is that if you're looking at a flux, but not just some random flux. Not just any flux, not a flux of any vector field, but a flux very specifically of a special vector field, a curl field. Right? I can view that flux instead as being a line integral, specifically a line integral around the boundary curve, the boundary of that surface. And, well, if you think about it then, if this flux can be computed as a line integral around that boundary, and if this flux can be computed as a line integral around its boundary, well, they have the same boundary. That means that the green flux and the blue flux, they're both computed by a line integral around their same shared boundary, and therefore the green flux is equal to the blue flux. Yeah. So that gives us this statement here. The green flux is equal to the blue flux because the green surface and the blue surface have the same boundary curve. All right, now I can't spend the whole lecture doing callbacks, but I am going to go ahead, and since it's so quick and easy, let me just point out that that's really morally equivalent to what we were doing when we talked about path independence. I mean, it's just a rip-off, it's one dimension higher rip-off of what we'd been talking about with path independence. So we have, on the one hand, the green curve, the blue curve, and they have the same boundary points. Right? And because they have the same boundary points, special vector field here being a gradient, this line integral and that line integral, they're both computed by changes. Changes computed on their boundaries, they have the same boundary. Therefore, they have the same change. Therefore, they have the same line integral, thus giving us path independence. And this is total rip-off of those ideas. Okay, so The analogies will continue. I will not continue to go back and point them out exactly. I'll make verbal references as we go along. But anyway, I encourage you as you're studying this section to, have the page, 3-4 pages back open and just kind of do like this. Okay, here's about surface independence. Oh, was there a symbol? Yep, same thing with path independence, just one step over in the diagram. And seeing that analogy go is really cool. Okay, so what we have here then is this is a remarkable property of a vector field. This is a remarkable property of this curl vector field. Curl vector fields have the feature that the flux is the same for any period. As long as the two surfaces have the same boundary curve, you always get the same flux. The flux, said differently, does not depend on the surface. It only depends on the boundary of the surface. So, if the value of the flux is independent of the surface, the term surface independent, I think, makes a whole heck of a lot of sense. So that's the term we're going to use here, surface independent. Vector field is surface independent if that's the case whenever the two surfaces have the same boundary curve. All right, and so with that terminology in mind, another way to say this is that curls are always surface independent. Yeah? Okay, so total ripoff of what we talked about with line intervals. Again, go back. Note all the strengths, the strength of all those analogies. Okay. All right. Now, does this arrow only go the one way? Hopefully it's no surprise that, no, it goes both ways. I'm not going to prove this. And this really is harder to prove. I sort of skipped over a motivation for the analogous fact about path independence. It was in the book. You can read it. It's, I think, very persuasive. This is much harder to motivate, and I'm not going to go talk about that here in this course. But it is nevertheless true that with the assumption that everything in sight is continuous and appropriately regular, no singularities or weirdnesses, that surface independent vector fields are also curls. Okay. All right. So let's make use of this. The example I'm about to do here is really, really analogous to the first example I did with path independence. So, you can look back and notice that as we go through this problem. It's a little different, of course. So, here's a vector field. And we have let's see here, a surface that's described by some discussion here. So we have a part of an elliptical paraboloid. There's the equation for the elliptical paraboloid. We want just the part that's above the xy plane, and by the way, it's oriented upward. So our domain for our flux is that oriented upward, and we want to compute flux. Additional information that we're given. We're given that our vector field is a curl. And because our vector field is a curl, that means that our vector field is surface independent. And that means that I can take this surface, right, and I can chuck it out the window, because I don't like that surface. I can chuck that surface out the window, replace it with any other surface I feel like. Right? Think aggressively. Right? Think about how can I maximize my convenience? What does my inner laziness want me to do here? Right? Pick any surface you want. The obvious stipulation, of course, it's got to have the same boundary. Right? So, got to have the same boundary curve. Any surface you want. So, even though you could maybe pick that surface, right, which is, I don't know, a little flatter. And you could, of course, obviously take things the wrong direction and make a glove surface. Don't ever do that. But the easiest thing to do, of course, right, is to pick this nice flat surface there. Has the same boundary. Yeah? Everybody good? Now let's think about orientations. You got to worry about this. I mean, orientations matter. Sorry, I was going to get a negative sign after that. So the surface we're given is oriented upward. Now, what does that tell me about the induced orientation on the boundary? We've got to play the right-hand game. And so think about if you looked at a normal vector over here close to where the boundary is, close but not on, it'd be like that. And now, thumb and right hand and swirls and all that. And I think you can see that the orientation on the boundary curve is that way. Yeah? Pretty good? So whatever orientation this new surface has, this yellow surface, it has to induce the same orientation on the boundary curve. So the green surface and the yellow surface have to have the same boundary, not just as points. They have to have the same oriented boundary. So same boundary and same orientation. So, okay, well, let's consider our options. And it's not hard to persuade yourself that if you oriented the yellow surface down, right hand, fingers swirl, it'd be going the wrong way. If you orient it up, right hand, fingers swirl, it's going the correct way. So the orientation on this yellow surface, also up. Everybody happy? Okay. A way that you can, let's see, let me say this is a kind of we call it a hack, that you can think this through. It's a sanity check, maybe. Is you can imagine the process of taking this green surface and slowly deforming it into the yellow surface. Imagine like it's I don't know, like a bouncy castle. You turn off the air, right, and the bouncy castle just slowly starts to deflate. Right? Well, as it slowly deflates, you can imagine this orientation vector. How would that go? As the thing slowly deflates, what would that deflate down onto? And it would clearly deflate onto the upward orientation. So that is a convenient trick that I hope you will find helpful, right? But don't make that argument on an exam. Think of this as a way to check your result. You have to argue on an exam about boundaries of the orientations on the boundaries. Okay. But this is a good way to confirm that you got it right. Okay, so phooey on that green surface. I never liked that green surface. I can now say, I'm just going to look at this yellow surface. Let's compute. You want the flux on the old green surface? Fine. I'm going to compute the flux on the yellow surface. It's going to give me the same flux because our vector field is surface independent. So flux on the yellow surface. Normal vector is real easy to write down. 0, 0, 1. Right, it's pointing straight up. That's clear. The vector field that we were originally looking at is this. That dot product's really easy to compute. The dot product is just xy. And so what we're left with is this double integral, which is susceptible to a symmetry argument, an easy symmetry argument. Therefore, our answer is 0. Right? So surface independence allows us to take a computationally inconvenient question and turn it into a clever observation. Everybody happy? Okay. What does this have to do with divergence? And let me point out, in this exercise, I had to be given that my vector field was in fact a curl so that I could conclude that it was surface independent. And what are the odds that you're going to be given this? How likely is it, do you suppose, that you're always going to know that something is a curl just, whenever it is a curl, that you will know that it's a curl? That's not obvious. Right? By the way, conspicuously lacking from my discussion of Stokes' curl theorem was how do you find an anti-curl? If y'all noticed that. When we talked about the fundamental thermal line integrals, we talked about how to find an anti-gradient. Why didn't I show you how to find an anti-curl? And the answer is it's really hard. And there's effectively no sort of reasonably accessible method that you can use in Math 212 to find anti-curl. So it is very hard to know if an anti-curl exists. So that makes this question, again, kind of manufactured, kind of artificial. Okay. But it turns out that there is a way to test, and it has to do with divergence. I'm getting ahead of myself. We're going to go back to this picture here. Right? Here's a picture of two surfaces. same boundary curve. By the way, notice the orientations. The orientation is upward on the upper surface, and it is upward on the lower surface. And you're going to be tempted to say, well, aren't those opposite orientations because one's inward, one's outward? Feels kind of opposite in some sense. That's not the question. Right? The question is, do they give the same orientation on their shared boundary curve? It's not a question of, as part of the boundary of the lump that they enclose, do they have the same size? That's not the question. It's what about the shared boundary that they have? Okay, so S1 and S2, as drawn here, one inward, one outward, give the same boundary on C. Okay, so that being said, if I give a name to the lump on the inside here, let's refer to the lump there as, how about L? Right? Then talk about what is the boundary of that lump L. It's S1 minus S2. And again, this minus sign is not an avoidable problem. There's a temptation to say, oh, well, the orientations are arbitrary choices. I'm just going to order S. I'm going to orient S2 downward instead of upward, and then I'll have a plus here, and then it seems more natural to do it like that. But keep in mind, if you orient this downward, then now S1 and S2 don't have the same boundary curve anymore. And that's the rule. If you want to talk about surface independence, S1 and S2 have to have the same boundary. So the fact that these have to have the same boundary curve means that their representations in the boundary of the solid will have opposite signs. So that is an unavoidable fact of geometry. So it's not something you can just kind of clever your way around. Note we made the same observation talking about path. Okay, so there's our picture. We have this lump. Its boundary is S1 minus S2. S1 and S2 have the same boundary curve. And let's go down here. Oh, I called it R. I called the solid R here. Right. So we're going to write down Gauss's divergence theorem as it applies to this solid R and its boundary, S1 minus S2. There's Gauss's divergence theorem. The boundary of R being S1 minus S2 allows me to rewrite the divergence theorem like this. And by the way, doesn't that look familiar? This is one dimension up, totally analogous to the equation that we had when we wrote down Stokes' theorem for considering path independence. And so we're gonna rip off the argument that we made there. Let's start off by speculating. Hey, what would happen if the divergence were zero? I mean, let's pretend if the divergence were zero everywhere. Well, if that integrand is zero, that means that triple integral is zero. That means the right side is zero. The difference, in other words, is zero. If a difference is zero, that means that these two integrals are equal to each other. That means we have a vector field for which these two fluxes with the same boundary curve are always the same. That means G is path independent. I'm sorry, I was thinking about path independence. Surface independent. So divergence equaling zero gives you surface independence. And the argument turns around backwards as well. If the vector field is surface independent, then these will always be the same. That means this difference will be zero. That means this triple integral will be zero. How is that possible? How could it be that a triple integral is always zero no matter what the domain is? The integrand would have to be zero. So surface independence implies the divergence is zero. Okay, shockingly analogous to the argument that we made at this stage talking about path independence. Okay. So again, three different ways of saying, three different properties that are shared by the exact same vector fields. Being a curl is simultaneous with being surface independent, which is simultaneous with divergence equaling 0. And recall, this is kind of what we predicted here. We started off using Stokes' curl theorem to make an observation about the existence of this notion of surface independence, which we asserted, well, I couldn't prove it, but we know is simultaneous with being a curl. And now, by using Gauss's divergence theorem, we see that a third equivalent condition is that divergence is 0. Okay, total rip-off of the equivalent arguments that we made in path independence. Talking about path independence, the fundamental theorem of line integrals motivating path independence as a property of gradients, which coincidentally, by our argument using Stokes' curl theorem, we argued that the curl is equal to 0. The exact same argument, one step over. Okay. I'm just going to go through the same example that we did previously, just that this time I'm not going to assume that this vector field is a curl. Right, that was the suspicious manufactured aspect of this example last time we saw it. I just asserted, hey, here's free information. Hey, here's the silver bullet that you need to slay this particular monster. How convenient, right? So now, no silver bullet at all. Here's a vector field. What are you going to do? Computing a flux. Well, you can compute the divergence yourself. Here it is. You can compute that divergence on your own. That's pretty easy. In fact, it's really easy algebra. We're taking an x partial of something with no x's in it, taking a y partial of something with no y's, and a z partial of something with no z's. It leaps off the page that this divergence is 0. And because the divergence is 0, that means that our vector field is surface independent. And that means that I can go through the argument that I did previously, and we've slayed the monster without the silver bullet. We made our own silver bullet. If you want to decide, the metaphor is not perfect, but you see what I'm saying. Yeah? Everybody good? Okay. One last observation I want to make about surface independence is it is arguably even more important than path independence. Now here's why. Path independence, by the way, I'm not trashing path independence. It's an extremely important concept, no doubt about it. But from a computational point of view, we have to recognize that anytime you can use path independence, well, that means that the function is a gradient. That means it does have an anti-gradient. And so you could just use the fundamental theorem of line integrals. So it's a powerful tool that allows you to solve problems for which you already have a powerful tool. So, how useful is that really? So it's like, it's a really nice screwdriver, but you already own a screwdriver. Whatever, it doesn't bring that much to your toolbox, as it were. I mean, it's a different point of view. It's a slightly different kind of screwdriver, right? So not that great. Surface independence, though, if you're trying to compute a flux, let me go back to here. Let me edit my diagram here a little bit. I don't know why I keep going back to the pencil mode. There we go. So path independence, this green tool that I have here. Hey, sort of path independence. I can change from one path to another path. As long as they have the same boundary points, doesn't change the value of the line integral. Nice, except I already have the blue tool. Fundamental theorem of line integrals. All I have to do is find the anti-gradient. Fine, no sweat. The game, win the game, no big deal. And you can, you already have a great tool. But let's take that argument and try to apply it to surface independence. Right, surface independence, the green argument. I can change from one surface to another surface. The flux won't change as long as I have the same boundary curve. the alternative of using Stokes' curl theorem would require not that I find an anti-gradient, which I know how to do. It would require that I find an anti-curl, which, as I just told y'all, we don't really know how to do. Right? So path independence is a screwdriver that's a little different from the screwdriver you already own. Surface independence is a hammer, and you do not currently own a hammer. So that's a handy pickup into your toolbox. Right? Does everybody see the point? Stokes' curl theorem, for the purpose of computing flux, unless somehow the anti-curl is just given to you, or maybe you get lucky in some way and can figure out what the anti-curl is, which you can't count on, Stokes' curl theorem, not such a great computational tool in that context. Okay, so arguably more important than path independence. Okay. Okay, moving along. This next section, lifetime theorems, there's not a whole lot of new material in this section. I really just want to organize some ideas that we already have. So I'll remind you of these diagrams. Right, here's our current state of our diagrams in R2, in R3. Right, and there's certain facts that we know. For example, I know that if you have a gradient field, if there is some function, you look at its gradient to give you a vector field, if you then compute the curl of that vector field, you will get 0. Right? Certain facts like that. And it turns out you can organize those facts into I think a nice little metaphor. It's just a metaphor. You don't have to take this seriously. In fact, I encourage you not to take this seriously. But I think this is a nice little memory tool. This is the way I think about these various theorems that I'm about to talk about. So this is ultra non-rigorous, right? But anyway, so here's my metaphor. I like to describe a life cycle of an integrand, and the life cycle goes like this. Let me just go to the picture. Suppose you take the curl of something and you get 0. What do you think the divergence of that 0 vector field is? Well, that's an easy calculation. The divergence of 0 is 0. So 0 is a state of non-existence which does not change over time. And I pose it's kind of like death. Right? So I refer to this as the vector field dies in column 2. Okay, it was alive here, non-zero, right? But then it died here. Okay. Now, let's suppose, and by the way, once something dies, then it stays dead. Right? Okay. All right. Now, let's suppose that we have some vector field and we take the curl, and suppose we got not 0. What would we say about this scenario? Well, it's alive here. We're calling this alive. It's not 0. How do we refer to the fact that it is the curl of a vector field from over here? Well, I would say, look, this was alive as well, and thinking of movement to the right as being passage of time, it survived. It didn't die. It didn't go to 0. 0 would have been death. This is not 0, therefore not death, therefore it survived. Here. It's just a metaphor. Okay, now let's speculate. What if we had some vector field and there is no anti-curl? I mean, what does this make you think of? If there is no there is nothing that survived to here. It's alive here, but it did not come from it's not a surviving previous thing. This is the first stage at which it's alive at all. My little silly metaphor is that it was born here. All right, so for example, you have a function, you take the gradient, you get another function, you take the curl, you get 0, it's born here, survives here, dies there. And that's just again, silly metaphor, but I think very satisfying in a weird, slightly morbid sort of way. All right? Okay, so with this little metaphor in play, here's what you can say. Everything has a lifetime of 2. This one statement tells you, like, there's like 8 different theorems that this kind of all encompasses. So everything has a lifetime of 2. Let's walk, and here's the 8 different theorems. But let me walk through these 8 different theorems here. If you have a vector field that is, if you have a vector field that is a gradient, then the curl must be 0. Well, yeah, of course it is, because if the vector field is a gradient, that means it survived. It means it was born previously. Lifetime of 2 means it dies here. Let's suppose you have a vector field whose curl is 0. Well, if it dies here, it couldn't have been born there. Then it would have had a lifetime of 1. So if it wasn't born there, that means it must have been born in the previous stage. That means when you have a curl that's equal to 0, that vector field must have an anti-gradient. Right, so these are results that we saw previously, the previously stated facts, but I'm just pointing out that they both can be kind of viewed as special cases of this more all-encompassing statement of everything has a lifetime of 2. So the silly metaphor of birth, survival, and death is it's a very nice little medium in which I can conveniently and compactly say everything has a lifetime of 2. Okay, so a couple of things I'll note. Every function has an anti-divergence. Again, we're assuming all regularity. Everything's defined, everything's continuous, everything's differentiable. I don't want to avoid deal with any issues of singularities. Every continuous function is the divergence of something. And the reason I know is because, well, there is no further stages after this. The universe ends after stage 3, and this is its lifetime of 2. That's the silly metaphor way to think about it, right? But so the fact that every continuous function has an anti-divergence, everything has a lifetime of 2. Likewise in the 2-dimensional cases, by the way. Right? So if you have a vector field, if Green's operator is 0, that means there must have been an anti-gradient, blah, blah, blah. Okay. All right. So, where am I going? Yeah, here it is. Everything has a lifetime of 2. Nice little memory tool. There is one exception. And extending the analogy, extending the metaphor to encompass this one exception is just a little more morbid than I can personally handle, so let's not, right? But here's the exception is constant functions. You have a constant function here. You take the gradient, you get 0. This poor little fella had a lifetime of 1. It's very sad. Okay, anyway, it's the only counterexample to my rule, again, assuming everything's continuous and well-defined. I don't want any singularities or anything like that messing things up. And by the way, it makes a big difference. It makes a tremendous difference. I'm going to say a couple of words about that in a minute, too. But there is this one exception to this rule, so heads up about that. That's the counterexample. And there's going to be a series of exercises that y'all are going to deal with when this fails. If your vector field maybe is undefined at a single point, like maybe you have a vector field that's undefined at the origin, all bets are off. All these statements previously go away. Not true. Right? So, like I say, there's an exercise which is it's one of these multi-part. I don't remember. I want to say it's maybe a 6-part exercise where you'll go through and do an exploration of what happens when there is a singularity at the origin. And it's weird. It's weird what happens. But anyway, the most important thing I want you to take away is that there is this very important requirement. If you're going to talk about these lifetime theorems, as I've stated them here, you can't have any discontinuities or points where it's not defined, anything weird, nothing bad. All bets are off. Okay, so a bunch of examples like we've already talked about. Sorry, skipped. I want to note how I've appended the diagrams a little bit here. So these are the final state. You might want to make a note, by the way, of this page number, page 453. This is where the final state of the diagrams is. You dog-ear that page or whatever. It's a really handy page to refer to. And notice our previous state of our diagrams. And I've just supplemented with these statements here. And the way I'm writing these statements is that solid lines represent the hypothesis, dotted lines represent the conclusion. So, if this, then that. Right? So the way you would interpret this first line here is if capital F is a gradient of some function little f, then capital F, you apply the green operator, you'll get 0. So each one of these lines in here represents an if-then statement. And these are sort of the different versions of the everything has a lifetime of 2 as represented on the diagram. All right. So a little bit of advice I want to give y'all. I think this is a good exercise. Let's see if I can fit this all. Oh, not quite. Well, anyway, close enough. There's a lot on that page. Right? This is just the R3 diagram. In fact, let me zoom out. I want to fit the whole thing. Here's our R3 diagram. There's a lot of characters on the page there. I would like to propose that you memorize all of this. And here's my second proposal. You may have inadvertently already memorized all of this. Okay? Because there's so many patterns, right? There's only a couple of things here that aren't just strictly consequences of patterns. So, for example, gradient, curl, divergence. You do have to remember that. You do have to remember that gradient takes a function and gives you a vector field. Vector field. And you do have to remember that when you take the curl of a vector field, you get another vector field, and that when you take the divergence of a vector field, you get a function. Those are facts you just have to memorize. But, hopefully you already remember those facts, right? You have to remember, I suppose, technically, that if you're looking at a vector field and a curve, that vector line integral is what we'd like to talk about. Well, again, I hope you've noticed that, if you give me a curve and a vector field, that's the calculation that we've been interested in all of Chapter 6, given those two inputs. So you have to memorize what these evaluations are. But again, you probably already memorized that inadvertently. Okay. You have to memorize the little pattern, right? The pattern is boundary, operator, evaluate on both sides, equal. Well, yeah, I really hope you've already picked up on that pattern, right? And so these theorems down here, even if you don't have them memorized, if you understand this pattern, and if you've noted what the objects and the players are on this top level of the diagram, you should be able to infer, guess, by way of this pattern, what each of these three theorems is. And then down here, everything has a lifetime of 2. So again, very strong pattern. So you might have accidentally already memorized this diagram, and I think it'd be a nice exercise for yourself to, after today's class, pull out a sheet of paper, blank sheet of paper, closed book, right? No notes. See if you can't reproduce this diagram. I bet you can. And if you can't, it really would be a good exercise. Whatever part of the diagram you can't figure out, you can't come up with, well, you definitely need to hit that part of the material a little harder to be ready for the test. Likewise for the R2 diagram, same pattern. You just have to remember that we're talking about Green's operator at that stage, right? You have to make sure that you understand what these evaluations are, And then it's the same patterns and the same lifetime theorems. So I'll bet that you probably already memorized this whole page. Okay. By the way, some of my students in past years have on the final exam, seemingly the very first thing they do when I say go at the start of the final exam, they turn the exam over to the back and they reproduce this diagram exactly as is on the back page of the final exam. It's the very first thing they do. Right? And then, as they're working through all the Chapter 6 problems on the final exam, which of course will be several, they have the advantage of having, what you might call the cheat sheet for Chapter 6 to work with, because they memorized it and wrote it down. So anyway, for your consideration, I think that's a good choice. If you don't write it down, at least make sure you have it in your mind confidently enough that you can think it through in your head when you're working problems. Okay, enough of that. Right. So let's see here. Where were we? Oh yeah. So I've supplemented the diagrams. Yeah. Okay. I remember where I was now. Okay. Suppose I want to compute a line integral. There's my vector field. I would like to, therefore, compute an antigradient. By the way, let's think about how the diagram tells me so. We're looking at a vector field of which I would like to compute a line integral. And therefore, in order to use this theorem, I would like to compute an antigradient. The diagram tells me. Right? Isn't it nice to see what you need to be interested in just by looking at the diagram? So, can I compute the antigradient? The lifetime theorem tells me I should compute the curl and see if I get 0. If I get 0, then there is an antigradient. And if I get not 0, well, everything has a lifetime of 2. If this is not 0, then it dies here. That means it was born here. That means there is no antigradient. Right. So, computing the operator that the diagram tells, let me just remind you what we were given in this speculation. We were looking at a vector field. We're going to compute a line integral. The diagram says compute the curl. Right? Here's where you are. It says do that. If you do, then whether you get 0 or not 0 over here tells you if there is or is not an antigradient over there. All right. So that being said, let's look at this vector field. Let's compute the curl of this vector field. By the way, here's my little cheat for computing curls. I think this is very helpful. Remember, a curl is a symbolic determinant. What's a cross product? It's a symbolic cross product, which is therefore a symbolic determinant, right? And what it is del cross the vector field. Cross is done with this symbolic determinant. So in your mind, just sort of superimpose this standard arrangement of objects over the vector field, first, second, third components, and start computing the determinant. Right. So you can see right here that you're going to want to do the y partial of yz, and then subtract the z partial of x squared z. That'll give you the first component. And then z partial of xy minus x partial of yz. And then finally, x partial of x squared z minus y partial of xy. So you can see right there on this picture what the calculation that you need to do to compute that curl. Is everybody on board? Now let me show you how you can save yourself loads of trouble. You can note in your head, without even writing anything down, that this vector field does not have an antigradient. Here's how I know this vector field does not have an antigradient. If it had an antigradient, the curl would be 0. If the curl were 0, all 3 of the components of the curl would have to be 0. But I can see in my head, without even writing anything down, the first component of the curl, which is z minus x squared, not 0. Right? If the first component's non-zero, the vector cannot be all zeros. Therefore, the curl is not 0. Therefore, there is no anti-gradient. So notice you didn't really have to write much down to come to this conclusion. At a glance, right? You can just remember that. That let's see. Well, I'm going to have to get the first element. I'm going to be taking the y partial of that. That gives me a z, and then minus the z partial of that gives me an x squared. That is z minus x squared. It's not 0. So don't waste your time on this question trying to find an anti-gradient, trying to play the game, hoping maybe that you can use the fundamental thermal line integrals. You can't. Yeah? Okay. All right. Alrighty. There's a similar little sheet that you can use sometimes. Let's look at this vector field. We want to compute a flux of this vector field, so we're requested. If you want to compute a flux, look at the diagram. We're given a vector field of which I want to compute a flux. It says compute the divergence. Okay. And I claim you can compute this divergence in your head. You're taking an x partial of a component that has no x's in it, plus a y partial of something that has no y's in it, plus a z partial of something that has no z's in it. So not only is the divergence equal to 0, it's computed as 0 plus 0 plus 0. It's not that the terms cancel to give you 0. It's that the terms are all 0, and it's painfully obvious at a glance that they're all 0. So super obvious that the divergence is 0 here. So heads up for little stuff like that. It comes up now and then. I'm going to let y'all read this example. It's pretty straightforward. I do want to say a couple of quick words about physics. These lifetime theorems manifest themselves in certain cool ways in physics, and y'all either have taken if you're engineers or physics or chemistry majors, you have, or pre-meds, you will have or have already taken E&M classes, at least one E&M class. And so hopefully you know the idea of electric potential energy, voltage. Right? Okay, so voltage is the thing whose gradient gives you the electric field. So voltage is the thing whose gradient gives you the electric field. Okay, another way to say that is that voltage is the anti-gradient of the electric field. How do we know that there is an anti-gradient to the electric field? Well, because the curl of the electric field is equal to 0 in the steady state. So the fact that you can even talk about electric potential, this is what they call the electric potential function. The fact that voltage as a notion, as a function that's defined in space as a location, the fact that you can talk about that is because of Maxwell's equation and the lifetime theorem. So anyway, I just think that's kind of a neat little context. Now I knew this when I was y'all's age, and I don't know, it hadn't been stated to me at the time as a statement about, no one said lifetime theorem. I made up that term. To my knowledge, I think I made that up. I'm hoping it catches on. If it catches on, I'm taking credit for it. So it hadn't been stated in those terms, but I knew this idea that, the curl is 0, therefore, right? What had not occurred to me is that because this idea of lifetimes applies everywhere in the diagram, there is an analogous notion for magnetic fields, one dimension up. So not the curl, but the divergence of a magnetic field is 0. That means that magnetic fields have an anti-curl. This anti-curl of the magnetic field is called the magnetic potential. Now, of course, it's a vector field. So it's not, they don't call it the magnetic potential function, it's the magnetic potential field. But it plays a role that's highly analogous to the electric potential function. So, in the same way that line integrals of the electric field work, in other words, can be computed as a change in values of the potential function voltage, right? So work is measured by a change in potential energy. Well, that's just fundamental thermal line integrals, that, changes in values compute line integrals. Totally analogous to that, flux of the magnetic field through a surface can be computed as a circulation line integral of the magnetic potential field. So anyway, it's kind of cool. Magnetic flux is definitely something that we're interested in, right? We saw last time magnetic flux is part of how electric generators work and how electronic braking works in hybrid cars. So it's a highly relevant notion and strongly related to this idea of a magnetic potential field. Okay, more on that in the physics class. A quick observation about domains. This is a little cuteness that's, I don't want to make a big deal out of this, and it's not really 100% true, but it's, the counterexamples are weird and far between, right? And that is that there is sort of a lifetime theorem for domains, not just integrands, right? So the lifetime theorems that we've talked about take place on what you might call that timeline. So if you have a function that it has a lifetime of 2 by way of the gradient operator and the curl operator, or if you have a vector field by way of the curl operator and the divergence, but on this little timeline, you might say. So it turns out there is also a kind of a lifetime of 2 in terms of the boundary operator on this timeline. It's not 100% true, but it's so close to true. So if you think about it, suppose you have a solid region. Okay, the solid region, the boundary of it is a surface. What is the boundary of a boundary surface? You can't have a boundary because, look, we're talking about a surface that encloses a solid. The process of enclosing the solid means you kind of have to close up. It means it can't have a boundary. You think about it, right? I was at a talk one time and the speaker referred to this fact and said, Theorem, Columbus, 1492. You can't sail off the edge of the Earth. The Earth is a solid. The surface is the boundary. There is therefore no edge to that boundary surface. The boundary has no boundary. Everybody see what I'm saying? Anyway, I thought it was funny at the time. He said it better than I did. And it works the other way around. So if you have a surface whose boundary curve is 0, if you have a surface that does not have if the surface doesn't have an edge, if it doesn't have a lip, how's that going to be? Well, it can not have a lip only by closing up, and by closing up, it then bounds a solid. Right? So my little abbreviation for this observation is every domain either has a boundary or is a boundary. And it's a nice compact little, succinct statement. So there's a surface. It has a boundary. Therefore, it can't be the boundary of a solid. It has a boundary. It is not on its own a boundary by itself. Here is a surface that is a boundary. Therefore, it does not have a boundary. Yeah? Everybody see what I'm saying? Likewise for curves. That curve has a boundary, so you cannot say that it is a boundary. It's not a boundary. It's not a boundary of anything. This curve has a boundary, therefore it's not the boundary itself of a surface. And likewise, here is a curve that does not have a boundary, or you might say its boundary is 0. This point positively and negatively going to cancel. You get 0 for your boundary. It does not have a boundary, and therefore it is a boundary. So anyway, kind of a lifetime of 2 statement in about domains. And now I do have to point out there is a counterexample involving knots, and this is really it's not terribly much to be worried about because I'm not going to tie any knots in curves in Math 212, so don't worry about it. You're probably not going to see any knot curves. It's weird, right? And furthermore, it is only because of our confining our attention to the mere three-dimensional world that we live in that knots even exist at all. If you were a mathematician in a four-dimensional space, you would scoff at the notion of a knot. There is no such thing as a knot in four-dimensional space. And if you want me to persuade you of that, come to office hours today. I'll be very happy to draw some pictures and persuade you that no matter what curve you think you've tied up into a knot, if you allow me to move through four-dimensional space, I can untie your knot. That's a fun little conversation. So anyway, so it's close enough to true. Every domain either has a boundary or is a boundary. Okay. Okay, yeah, so 9 parts. There's 9 parts to this exercise here about the punctured plane. So what goes wrong when you have a vector field where it fails to be defined at a single point? So I give you here a vector field that fails to be defined at the origin, and something goes terribly wrong. And I guide you through the entire discussion in these 9 parts. Okay. All right. Okay, this last section, again, not really much new material. This is really just a bunch of examples. I'm going to try to hit as many of these examples as I can, but y'all can just read the rest of these examples. It's basically just kind of bringing together all the ideas that we've talked about. We've talked about a bunch of different boundary theorems. We've talked about a bunch of different what I call lifetime theorems about how these operators relate to each other. There's loads of patterns. Everything is a lot like at least several other things in this chapter. Right? And this is just kind of sort of putting it all together and observing how you can use these ideas to actually, turn the crank. How do you actually compute line integrals and surface integrals using these ideas? So the first thing I want to talk about is diagnosis. There's a cheat that a lot of textbooks use. I tried to avoid this as much as possible in my book, but I'm sure I did a little bit. And that is, let's say in the section on the divergence theorem, look at the exercises, and there's a bunch of exercises in there which involve using the divergence theorem. Well, of course they do, right? So students are sitting there and they're cranking out and they're pounding out these questions that involve using the divergence theorem because they know, hey, this is the section on the divergence theorem. This exercise, I assume I should be using the divergence theorem, right? And then those students get to the test, and the question says, hey, compute this flux. And there's no context. This is not in the section on the divergence theorem. It's just hey, compute this flux. And the student's like, well, should I use Stokes' theorem? Should I use the divergence theorem? Should I use chapter 5? Should I use symmetry? What do I do? Right? There's a bunch of different possible methods. How do I know what to do? So very often textbooks will make a list of questions, and it's deceptive to the students because because very often the textbooks will kind of not make students actually diagnose, actually figure out, wait a minute, what kind of a problem is this? So I want to talk a little bit about how to diagnose, and it's pretty much a matter of looking at the diagram and making appropriate inferences. So for example, let's suppose we're in R3. Let me rephrase that. Suppose you've been asked to compute a line integral. Suppose the vector field in question, of which you want to compute a line integral, has 3 components. Therefore, you are in R3. Right? So you're not in R2. Don't compute Green's operator. You can't compute. There is no such thing as Green's operator. We're not in R2. We're in R3. Okay. All right. So to diagnose what kind of a problem this is, you have a couple of candidates. You might use the fundamental theorem of line integrals. Now, how do you know? Well, there's 2 things you would need to be able to use the fundamental theorem of line integral. You'd have to take the curve in question and look at the boundary. That's never an issue. If you give somebody a curve, it's got a starting point, it's got an ending point. Possibly the same 2 points. But anyway, the point is you can talk about the boundary, and that's just a matter of looking at it. Okay. What is not obvious is, can you find an anti-gradient? Right, that's the stumbling block. That's the asterisk on the fundamental thermal line integrals. If you want to use this fundamental thermal line integrals, you need an anti-gradient, and no, man, we might not consider it's possible we might not have an anti-gradient. So that's the potential stumbling block, and you resolve that, of course, by computing the curl. If you compute the curl, if you get 0, then yes, there is an anti-gradient. If you don't get 0, there is no anti-gradient, and don't bother looking for it. It's not there. It's a wild goose chase. Yeah? Okay. All right. So that's how you decide whether you can or can't use the fundamental thermal line integrals. Okay. Now, what about Stokes' curl theorem? Suppose you, again, we're trying to compute this line integral. Suppose I want to use Stokes' curl theorem. Okay, well, I've got a vector field given to me. Can I compute the curl of that vector field? Sure. It's just some partial derivatives. There's no question as to, like, you know, whether there is a curl. There's a formula. Plug in. Of course you can compute the curl. The question is the curve over which you're computing this curl. Can you find an anti-boundary? Is that curve a boundary of some surface? Right? Is there a surface whose boundary is that curve so that you can use Stokes' curl theorem by computing a flux through that surface? You've got to have that surface in order to invoke the theorem at all. Right? So that's the asterisk on Stokes' curl theorem. Is there an anti-boundary? Now, per the observation I just made, you can resolve that by looking at the boundary of the curve. If the curve has two distinct boundary points, if it has a boundary, then on its own, you can't say that it is a boundary. There is no anti-boundary. Right? On the other hand, if the boundary is doesn't exist, right? If the boundary is 2 points that cancel, the same point twice with opposite signs. If the boundary is 0, then there is an anti-boundary. And then now how you find it is you look at the picture and you think geometrically. Right? There's no algorithmic process for finding an anti-boundary. You just look at the picture. Okay, so that's the diagnosis process. You've got then these two candidate theorems, right? If you're interested in computing a line integral, here's your two candidate theorems. Compute the curl of your vector field. Think about the boundary of the curve and see what's 0, what isn't 0, and deduce from that way which of these two candidate theorems you might or might not be able to use. Everybody see the process? Right? It's the same thing for up here. Same thing up there. Right? If you want to compute a line integral in R2, take Green's operator of the vector field, take the boundary of the curve, or think about these things, and whatever is 0, whatever isn't 0, allows you to deduce which of these two theorems you might be able to use. And then likewise over here. Right, take the vector field, compute the divergence. If you're being asked to compute a flux, notice, take the divergence of the vector field. Think about the boundary curve of the surface and deduce which of these two theorems applies. Okay. So I do want to make one observation. Don't waste your time in this scenario where you've been asked to compute a line integral. Do not waste any time with taking this vector field and computing the divergence of it. That doesn't make any sense. Right? Why would you take the divergence of that vector field? And yet I see this every year. The question says compute the following line integral, and students will compute the divergence. That serves no purpose. And all it does is make it look like you don't know what's going on. Right? So please don't waste your time with that. Also, notice there is not going to be any triple integrals. Right? If you're computing this line integral in R3, any triple integral on the page makes you look bad. Right? There's no way that's going to come up. Right? So I don't want to see any triple integrals. Right? I don't want to see any divergence if the question is about computing a line integral. Okay. All right. And so again, conveniently, the diagram tells you that, right? The diagram, here's what we're computing. These are the two theorems that are next to it, and none of this stuff over here could possibly come up. So it's an easy rule to remember, right? So anyway, lots of, does a lot of work for you. Let's see, where am I? I was on the other screen here. Yeah. Okay, so, so roughly speaking, this is your process. Where are you on which diagram? Compute the appropriate operator, right? Think about the boundary. And you get to determine from that which, whether the theorem on the left or the theorem on the right might apply. If one of them applies, cool. Right? If both of them apply, sweet. Right? If neither one of them applies, okay, well that's too bad. If neither one of them applies, right, so the curve is not a boundary and the vector field is not a gradient, well, then you've got yourself a chapter 5 problem. Right? And that's okay. I mean, sometimes you have to parameterize and plug and chug. But you'll know you're doing the right thing, right, by having gone through this process and checked that neither of those boundary theorem applies. By the way, of course, with Chapter 5, it's not just the parameterized method. I mean, you can also look for symmetries, right? I encourage looking for symmetries. Look for geometric coincidences. Look for the possibility that maybe, the orientation vector and the field vector are always perpendicular everywhere on the surface. Sometimes you get lucky, right? So always heads up for that kind of thing. So symmetries, geometric coincidences, and then if all else fails, parameterize and plug and chug. All right, so I have a bunch of examples, and I have 2 minutes. So what I'm going to do is, let's see, do we have time to start? Yeah, I can do this first example. It's pretty quick. And then we'll do some more of this on Monday, because I do want to spend some time finishing this up. So here we have a vector field. We're computing a line integral. This is a vector field in 1, 2, 3 dimensions. So we're looking at a line integral in R3. That means we're looking at that. We need to compute the curl, hoping for a possible anti-gradient, and we need to think about the boundary, hoping for a possible anti-boundary surface. Alrighty, well, the curl is 0. That's a straight-up calculation. You take this vector field, compute the curl of it. That's just a little algebra. Let y'all do that. The curl is 0. Fundamental thermal line integrals is on the table. So we got 0. There is an anti-gradient. I can use the fundamental thermal line integrals. Yeah? Okay. On the other hand, now before we just dive into that, let's consider the possibility that we might have another option. What happens if I take my endpoints? Take 0 and 1. Plug into this function. Where does the curve start? Where does the curve end? And they're not the same. Again, that's just a little bit of arithmetic. This curve starts and ends at different points. This curve has a boundary. Therefore, it is not true to say that this curve is a boundary. So this curve is not a boundary of anything. There is no anti-boundary surface, so you cannot use Stokes' theorem. Going back to the diagram, we did not get 0. Therefore, there is no boundary surface, and you cannot use Stokes' curl theorem. So your options are fundamental thermal line integrals, anti-gradient, play the game, or Chapter 5 methods. And so looking at those options, which would you rather do? Would you rather find an anti-gradient? Hey, this is just polynomials. That looks harmless. I'll bet you we can find the anti-gradient pretty reasonably. On the other hand, oh man, look how ugly that parameterization is. Do I really want to take that and plug it into here and instead plug and chug, pass? Right? Do I see any obvious symmetries? No, it's not. Right? So fundamental thermal line integrals, by far the most natural observation, the most natural option that we have. So use the fundamental thermal line integrals. Okay, I'm going to do several more of these diagnosis sort of strategic examples on Monday. And a quick reminder, I will not be here on tomorrow. So I'm going to have a sub coming in. He's an experienced Math 212 teacher. He's going to do a great job I'm sure. And if you have any questions about that process, anything related to that substitute, come talk to me after class. See y'all later.